here we're going to calculate an instantaneous rate of change. So we know from previous lessons that the average rate of change is just the slope of a line between 2 points on a graph. The instantaneous rate of change is the slope of the tangent that touches the point on that, or touches a point on that graph. So yeah, that's called the tangent line. So in order to do this, first of all, from a graph, let's just go through this question. So the graph below shows a population growth since 2006. Find the instantaneous rate of change in 2008. This question might look similar. It's the same as the previous lesson. It's just for instantaneous rate of change now. So t equals 0 is 2006 as per the question. So this is 2006. That means this is 2007, 2008, 2009, right? So we need to find the instantaneous rate of change in 2008. And really, the only way to do this from a graph, if we're not given an equation or anything, is to sketch in a tangent line. And in order to sketch in a tangent line, really, I have a ruler here, see this? Really the easiest way is to grab a ruler and to sort of just find that point. So actually, let me just go to that point on the graph, 2008. So we're looking at that point right there, right? And we basically want to put that ruler down, touching that point, just touching the graph. Remember, picture there's like a snowboard around this graph. Where would the snowboard be pointing, right? So for example, that touches that point, but it's not tangent to that point, right? It goes through the graph. Same thing with this. This might look a little bit too steep. We want it just to go sort of in line with the graph there. Another way to think about it is if you were to zoom in really close to the graph, see how the line looks like a straight line here that sort of goes like that. We want to basically find out what the slope of that line is. So there's our ruler. And if we look, I can actually draw right along the ruler. Look at that. This is a new feature that I'm just trying out now. So the point is we got to try to find the slope of that line, and that's equal to the slope of the tangent or the rate of change of the graph at that point. There, I was able to get rid of the ruler. So in order to find the slope of that line, we basically just need to find the rise and the run, right? Because the instantaneous rate of change, IRC, is going to approximately equal the delta y, the change in the y, over the change in x of that line. Remember, this is approximation because it's just from a graph. That isn't the exact tangent, but something close to it. So let's look. So the change in y has gone from 0 to 400. So this rise is just 400. That's our delta y, or our change in y. And then our x has gone from 0.5 to 3.5. So that's gone up by 3. Right? I think so. 1, 2, 3. Yeah, that's right. So if we just plug those numbers into our graph, our delta y is going to be 400 divided by 3. This gives us a value of 400 divided by 3 is 133, approximately 133. Again, we need to include units here. So remember, the y part is population, so people basically, and the x part is years. So the unit for this is 133 people per year. I'm going to put ppl per year. Now, if you look, the answer to the question up here is 150 people per year. So maybe we didn't draw the line right on. It was a little bit off. It's just an approximation, but for this sake, it's a pretty close approximation to what the answer actually is. To get more accurate, we're going to need to start using the equations. And just to remember what this actually means, this means basically in 2008, the population was changing by 133 people per year. So basically, 133 people were coming into this town or being born in this town per year, right? And if we think about how that's changed over time, 2006 would have a tangent that looks something like this, right? So it's a little bit less steep. And 2009 would have a tangent that looks something like that. It's a little bit more steep. So we can say that the population is growing faster and faster as time goes by. So here's a problem where we're given a table and we're asked to find the instantaneous rate of change at t equals 2. So basically, what is the rate of change at this point, right? How fast is the population changing at that point? How are we going to do this? I'm going to start off with just a very quick sketch of what's happening here. If we look, this graph, it starts at 800. So if this is time and this is population, it looks like the time starts at 0 and the population is 800, and it's decreasing, right? So it's going to look something like that. Actually, let me just do that in blue. It's going to look something like that. I don't know exactly what it's going to look like, but in general, something like that. And we're asked to approximate the population at 2, right? So if I just zoom in there, we're asked to find basically what the change in population is at 2. So we're looking basically for the slope of that tangent line, which I've just sketched there. Now, the problem is we don't have too much information about this. How are we going to go about approximating this? And really, the way to do it is to look what other data we're given. Look at what other data we're given. So we're not only given that the population at 2 is 652, but we're given what the population is at 1.5 minutes and 2.5 minutes, right? On either side of that. So if you think about it, if we wanted to find, if we wanted to approximate what that population is, so 2.5 would be something like here, right? And 1.5 would be something like there-ish, like there. So even if it's not exact, we could look at what the population is at 2.5, right? And if we connect those two, if we look at basically the secant between those two, it's going to be very close to the tangent, right? Alternatively, we could do the same thing with 1.5, right? We could find what the population is here. Well, we know what it is. It's given in the table. And look at this secant here. And that, again, is going to be very close to the slope of the tangent, right? Because those are the two closest points to it, this is something we can do. So to try to get as accurate as possible, that's essentially what we're going to do. We're going to find the slope of each of those segments. I'm going to call it M1 for slope of that little segment there, and M2, slope of that little segment there. And then we're going to compare them and see if that can help us approximate what the slope of the tangent is at that point, okay? So M1, the slope of M1, is going to be just our change in y over our change in x between these 2 points, right? So what's our change in y? It's gone from 737 to 652. So we're going to do y2 minus y1, so 737. Basically, we're using the average rate of change, right? 2 minus 1.5, right? And that gives us an M1, a slope 1 of that little segment of negative 170. And it's bacteria per minute, right? So let's do the same thing with M2, that second little segment there. And here, actually, you know what? I'm going to do it in blue, M2, because that is the difference between these two right here, right? So again, it's going to be delta y over delta x, change in y over the change in x. It's going to be 515 minus 652 over 2.5 minus 2. And this, if you do this in our calculator, will give us negative 274 bacteria per minute. Okay, so now we have the slope. Remember, let's go back here. We have the slope of M1, so it's this little segment here, right? And that is negative 170. And we have the slope of this little segment here, blue. We calculated it in blue. So it's that little segment there is negative 274. So how does this approximate the slope of that tangent line? Well, maybe one way to do it is we know it's steep. The graph is steeper here, right, in this first segment right here, and it gets more steep here. So the slope of this tangent is probably going to be between those two slopes. So one way we can do this is to approximate it by finding the average of those two slopes. Okay? So we're gonna approximate the IRC is going to be approximately equal to the average of those two slopes. So the average, remember, we find it by adding those two things up, 170 plus negative 274, divided by how many things there are. So there's two of them that we're taking the average of. So we do this calculation, and we get negative 222 bacteria per minute. So this is one way from a table to approximate the instantaneous rate of change, just by looking at those little secants before and after, and then taking the average of them to find or to approximate the instantaneous rate of change. It's not going to be exact, probably. If we used a computer model to generate a curve and then find the tangent, it's probably not going to be exact, but it is close. And you'll see how we can do this a little bit more accurately in the next section when we're given an equation. So here's how we find or we approximate the instantaneous rate of change from an equation. And we do this with something called the difference quotient. So let's look at an example. This green graph here, I'm just going to take out my ruler. Let's say we wanted to find the slope of the tangent at 1, where x equals 1. So basically, just to sketch that in, we want to find the slope or approximate the slope of that tangent, right? Let me hide that ruler. So the way we do that, is by using the difference quotient. And just like we did in the previous question, by the way, you should have watched the previous video on secants, tangents, and difference quotient. It gives you some sense of what this is, right? And essentially what we're going to do is we're going to approximate the tangent, we're going to approximate the slope of the tangent by, if we're looking for this point right here, we could, for example, find the secant between 1 and 3, right? So the slope of the secant there, that's a decent approximation of that tangent line, right? We could go even closer. We could do the secant between 1 and 2, right? See how that's even closer to the slope of the tangent? But if we wanted to approximate the tangent even more, we can zoom in on that point. And let's say we wanted to find the slope of the tangent between 1 and like 1.01. So we wanted to find the slope of that little tiny line there. And that's going to be very close to the slope of that tangent line. And essentially that's what we do. We find that difference. And we call that difference, actually, that difference between 1 and 1.01, whatever that is, we call that h. And in this case, I've used h as 1.01. Sorry, no, not 1.01. There's my eraser. Just 0.01, because that's the 0.01. That's the difference between those two values. We could, if we want to be a little bit more accurate, we could make that 0.001 or even 0.000001. Basically, it comes down to how much time do you got and how accurate your calculator can be in order to calculate that. But the smaller the number is, the more accurate this is going to be an approximation of that slope. So the equation we use to do this, it's basically the same thing as before, as finding the average rate of change between 2 points. So it's still delta y over delta x, a change in y over change in x. And the change in x, that's the easy part, right? Because that's just how much the x value has changed between those 2 points, which we're just calling h. The y difference is what the function is at x plus h. So in this case, x plus h would have been that 1.01, right? So what's the function equal to at 1.01? And then we're going to subtract what the function is at 1. So essentially it's the same equation, and that's what we use for the difference quotient. So let's see what this looks like in practice. Let's do an actual problem. Okay, so we're asked in example 3 to approximate the instantaneous rate of change for that function at x equals 2. So our first step is to apply the difference quotient. Whenever we want to find the instantaneous rate of change, we can apply the difference quotient. So I'm just going to write out the formula for the difference quotient. I'm going to put IRC, instantaneous rate of change, is approximately equal to f at x plus h minus f at x all over h. Okay, now I plug in my function. So my function there was 0.5x squared minus 1. Now, if we want to evaluate the function at x plus h, that's going to be, 0.5. And instead of x, it's going to be x plus h, right? Squared, minus 1. And then the function at f of x is just going to be the function. So 0.5 x squared minus 1. And we put this all over h. I'm going to... as h. Okay, so now, in order to find or approximate this instantaneous rate of change, let's just plug in what we know. We have our expression. We can just plug it in. So we know we're going to plug in our x value as 2 because that's the location that we want to find the instantaneous rate of change, right? So I'm just going to put this off to the side. X equals 2, and our h, let's make it 0.001. Just a small value, and let's see what happens when we plug those things in. So 0.5, 2 plus 0.001 squared minus 1 minus 0.5, 2 squared minus 1, all over 0.001. Okay? When we do that in our calculator, we get 2.0005. So usually we don't carry that many decimal places. Let's round to 3 decimal places, or 2 decimal places, which rounds to approximately 2. Remember, this is approximate. So it comes out to 2, essentially. If we look at our answer, the exact answer here is 2. So if we were to use some calculus to find the exact answer, that's what calculus does, we would get that it's 2. We came out very, very close with 2.0005. So you see, you don't need to plug in an h value that's that small. 0.001 will mostly work unless you're already dealing with very, very small numbers, in which case you should use an even smaller number for h. So that's the process. Let's apply it to a few more questions. Okay, here's another question. So it asks us to find the instantaneous rate of change at 3x squared minus 4x plus 8 at x equals 2. I'm going to change up this question by adding a part. So we're going to find the rate of change at x equals 2 and x equals 3. So we're just going to make it a little bit more long, basically. So let's start off with our instantaneous rate of change. So the difference quotient says it's going to be f at x plus h minus f at x all over h. And we just plug in our formula there. Every x we're going to replace with x plus h. So 3x plus h squared minus 4x plus h plus 8, and then subtract the regular function, just f at x. 3x squared minus 4x plus 8 all over h. Okay, so last time we just plugged in the values we know, but this time we have to plug in 2 separate values, 2 and 3, right? We need to know what both of those rates of change are. So before just plugging them in, it might be a little bit easier to just simplify that expression first. Okay, so let's try that. Let's try to simplify this whole expression to make it easier for us down the road. So that's going to be 3. I'm going to simplify this, x squared plus 2xh plus h squared minus 4x minus 4h plus 8 minus 3x squared, barely fits, plus 4x minus 8. Whoa, that looks crazy. But look what happens. Already, this 4x and this negative 4x and that 4x are going to cancel out. This 8 and this negative 8 are going to cancel out. So it's already gotten a lot simpler just by canceling a few little things out. And this actually happens a lot when we deal with these things. Okay, so let's continue. Continue simplifying. 3x squared plus 6xh plus 3h squared minus 4x minus 3x squared all over h. Oh, again, this and this will cancel each other out. That makes it a little bit easier. Oh, I made a mistake. Do you see where it is? This should actually be 4h here. So this should actually be 4h. Sorry about that. So let's simplify. Simplify even more. So 6xh plus 3h squared minus 4h all over h. What do you notice about the numerator? All the terms have h in it, so we can actually factor out an h. That's the only thing we can factor out, I think. 6x minus 3h minus 4 all over h. And then we see that those h's cancel out. So the final simplified version of this, of the difference quotient, is 6x minus 3h minus 4. That's much simpler than this thing up here, right? Notice how those two things are equivalent to each other. Just one is a lot simpler. So when we need to find the instantaneous rate of change, remember, this represents the instantaneous rate of change, or it approximates the instantaneous rate of change. So if we want to find the slope of that function, the instantaneous rate of change at 2 and 3, it's much easier to use this, to plug in 2 and 3 into this, as opposed to plugging them both into that original function. So often I'm going to have you simplify the difference quotient before plugging in values. So in order to do it, let's do it at 2, at x equals 2. The instantaneous rate of change, we'll use h equals 0.001 again. So let's do that. This is going to be IRC is approximately equal to 6 times 2 minus 3 times 0.001 minus 4. That gives us 7.997. Okay, and if we round that to 2 decimal places, that's going to be approximately 8.00, essentially. Okay, not bad. And at x equals 3, we'll use h as 0.001 again. We have IRC is equal to 6 times 3 minus 3 times 0.001 minus 4. There's a little bit messy there. But what we get is 13.997. Okay, which is approximately equal to 14. They won't always come out to nice numbers like this. It just so happens, I'll make it 14.00. It just so happens in this question that it does. Okay, so there we go. We found two different difference quotients, or sorry, two different instantaneous rates of change of a function by simplifying the difference quotient. So the next question asks us, going back to example 4, determine the equation of the tangent line at x equals 2. So let's think about what we've found so far. First of all, we know we have a quadratic here. So that function that we're given in the previous question is a quadratic. So it'll look something like that. I don't know exactly what it looks like. I'm just drawing it. It opens up and whatever. Doesn't matter. We want to know what the equation of this tangent line is at x equals 2. So say that this is 2 here. Our tangent line at this point is going to look something like that, right? It's going to just touch at that one point. So we want to know the equation of that line for this question. What's the equation of a line? Y equals mx plus b, right? So that would be the equation of that line. What do we know about that line, though? What have we found so far? Think about what we found in the previous question. We found something at x equals 2. What did we find? Remember, we found the instantaneous rate of change at x equals 2. And we found out that that was equal to 8, right? Remember what the instantaneous rate of change is. The instantaneous rate of change is just the slope of that line, right? That just touches at that point. So we know the m for this is going to be 8. Okay? That's the point of what we did in the previous question. We found the slope of that tangent line. So we know that equation is essentially going to be y equals 8x plus b. We need to find now the other part of that equation, b, which we should know is the y-intercept, right? How do we find the y-intercept? Well, if we know a point on that line, we can just substitute it into that equation. Luckily, we can find a point on that line, right? We know that that is a point on the line where x equals 2. So what is our function at 2? We can just plug that into our original equation, 3x squared minus 4x, so 2 squared minus 4 times 2, what was the third part? Plus 8. So that equals 12. So that tells us this point on the line is going to be 2, 12. Right? Obviously, I didn't draw it to scale because that's a positive value, but it doesn't matter. So 212 is on the line. So basically, in order to find b, we can just plug in 0.212, right? So 12 equals 8 times 2 plus b, and, oops, that should be an equal sign, and that makes b -4. So the equation of our line is going to be y equals 8x minus 4. There we go. That's the equation of that tangent line. So we needed the difference quotient to find this part of it, and then the slope, basically, of that line. And then we used just a little bit of algebra to find the y-intercept. So for example 6, I want you to try it yourself. Pause the video here, try it yourself, and one other thing I want you to try to do, I want you to try to simplify the difference quotient instead of just plugging in things at the beginning. This just gives you a little bit of practice with algebra, and you're going to see this algebra coming up, so it's important you practice it. So pause it now, and then unpause it when you've found a solution. Okay, there's the answer. That is a lot of algebra, and I didn't do it the most efficient way. You may be able to do it a little bit more efficiently, but it just has to do with simplifying fractions, canceling some stuff out, and you get your final simplified difference quotient looks like this. Not actually that simple, but when you plug in x as -1 and h as 0.001, I got my instantaneous rate of change at that point is 3.003, or approximately 3. Okay, let's move on to this last problem. This has the trajectory of a toy rocket given by an equation where s at t is the distance above the ground in meters and t is in seconds. So it's asking us basically what the instantaneous velocity of the rocket is at t equals 4. So it wants to know the speed of the rocket at 4 seconds when we are given the equation for the distance. And one thing to keep in mind, this is a physics concept, but it's pretty straightforward. The instantaneous rate of change of a distance graph or a distance function is velocity. Because think of distance as just how distance or velocity as how distance changes per time, right? So if distance is in meters, velocity is going to be meters per second, how that velocity changes per time. So that's essentially all we're finding here. We just want to know the instantaneous rate of change of that function s at t equals 4. So pause it here, give it a shot. Simplify the difference quotients as much as possible before plugging in t and h, okay? Unpause it when you're ready and I'll show you what we got. So after doing the algebra, it should your difference quotient should come out to -10t minus 5h plus 30. And look back at the question. We want to know what the velocity is at a t of 4. So we want to know this at t equals 4. And an h value, why don't we just use 0.001 again? It seems to be working for us so far. And this question is not much different than the previous ones. If we plug that all in, we should get a value of -10.005. Let's think about our units for a second. Remember, the distance graph, or the distance function, sorry, was in meters. And what we did is we found how this changes with time, right? So time is measured in seconds, so essentially this is meters per second. It's the change of the displacement per second. If we check back up here, look what the answer was on the page, -10 meters per second. Now, what do you think the negative means there? Think about it. What does the negative mean? Well, to do that, let's think about what positive and negative mean in terms of the question, right? So the trajectory of the rocket, so the path of a rocket basically is modeled by that equation. So the st at t is the distance above the ground. So if the distance above the ground is changing in a negative way, one way to think about it is that it is moving towards the ground, right? It is getting less high by 10 meters every second. So it's basically falling at a rate of 10 meters per second at a time of 4.